We will begin momentarily.
Good evening, everyone, and welcome to today's session of the Biostatistics and Research Methodology program. Our focus for this session is on a critical area of research, inferential statistics and hypothesis testing. These tools lie at the heart of scientific inquiry, helping us move beyond data description to drawing meaningful conclusions and making evidence-based decisions. We are honored to have with us Dr. Mojeed Akorede Gbadamosi, a distinguished public health scholar and seasoned biostatistician with over 2 decades of academic and research experience. Dr. Gbadamosi is a fellow of the Africa Institute of Public Health Professionals and currently serves as lecturer and biostatistician at the University of Rwanda. Throughout his career, he has taught and mentored countless students in biostatistics and epidemiology, coordinated impactful research at the School of Medicine and Pharmacy, and contributed extensively to scholarship on non-communicable diseases such as diabetes, hypertension, obesity, and nutrition-related conditions. His publications in leading journals, including BMC Public Health and Global Health Action, as well as his roles as peer reviewer and expert advisor, reflect his deep commitment to advancing public health knowledge and practice across Africa. Through teaching, research, and service, Dr. Gbadamosi continues to champion the application of biostatistics as a tool for improving population health and informing policy. It is therefore with great pleasure that I invite him to lead us in today's session. Dr. Gbadamosi, the floor is yours.
Good evening, ladies and gentlemen.
Yes, sir.
Good evening, sir.
Good evening, sir.
Okay. You are most welcome to this session. This is the fifth session that we're having. We started in April. I started the presentation. Very honored to be with you so that we look at an important topic in biostatistics and research methodology. So that is inferential statistics and hypothesis testing. Last month, we were privileged to be with my learned colleague, Dr. Felix, who took you through descriptive statistics. So we're going to continue from where he stopped. So we're looking at inferential statistics and hypothesis testing. I have to make some quick disclaimers before I start. I know there are some researchers, seasoned researchers and colleagues online. We also have students and we have practitioners. Those who are familiar with biostatistics know that inferential statistics is very broad. So there is no way someone is going to do justice to that huge topic in less than 2 hours. Nevertheless, I'm going to try my best to address key issues, and we're also going to accommodate everyone. Some of my students are online. I've seen some of them. Those who are familiar with inferential statistics know that we're going to bother you with some calculations and some diagrams, which are not too good looking. I've decided to make it as simple as possible so that we can all relate to the concepts, whether you have background in biostat or not. So that's the approach that we're going to use. So let's go to the first slide. Let's go to the first slide. And that's where we have the unexpected survey. Thank you. Suppose a survey of 50 people finds that 40 prefer tea over coffee. Can we claim that most people in the city prefer tea? So I need you to type in the chat yes or no, or if you think that we need more data. So I need this response from you in a few seconds. Type in the comment section what you think. Okay, Ebiloma said yes. Kennedy says cannot see your screen. Linda says no. Solanke said yes. Irat Balogun said yes. Ali said no. Okay, that's fine. Let's go on. Let's go on. I've seen the reaction. Thank you very much. This is excellent. Okay, so we we are starting with a dilemma, because some participants said yes, we can conclude. Other participants said no, we cannot continue. So this question that we have started with, Dr. Gladys, you are recognized. It underscores and introduces you to the concept of sampling and in statistical inference. So that's what we are trying to show. I'm not going to tell you whether those who said yes, whether they are correct, or whether those who said no are correct. You are going to tell me that one by the time we are done with this discussion. But you can see the issue with biostatistics or statistics generally. So we have two groups now. Some people said yes, other people said no. So let's look at our outline because of time. Now, we're going to look at the foundation. Let's go to the next slide, foundation. We'll look at the foundation. Next slide, please. Mira, can we go to the next slide? Linda said it depends on the sampling method. Okay, let's go to the next slide. Thank you. So the outline. So we are looking at the foundation. Why do we need inferential statistics? Then we look at the interpretation. So we're going to interpret p-value and confidence interval. These are two key statistical measures, and they are, aside from the fact that they are widely used, they are also widely misused, especially the p-value. So we're going to look at this. Then we look at some common pitfalls that we need to be aware of. What are the common errors in interpretation, and what are the common errors in practice? So we are going to see some excerpts from published articles in peer-reviewed journals, and the mistake that we expect you to avoid as researchers. Kennedy is saying you cannot see the screen. Mira and IT, can you help us? Okay, so let's go to the next slide. We will look at a framework that also tells you which statistical test is more appropriate for which research question. So now let's get started by looking at the fundamental problem. In the real world, data has what you call variability. We know from the different discussions that we have had that we usually don't deal with the entire population. We sample. We also know that in statistics, we have descriptive aspects, which we have discovered. We also have inferential statistics, which is where we are today. So there is that variability in the real world data. For example, not all patients respond to the same way to a drug. You administer a drug to different patients, they have different reaction or response to that intervention. Not all cell culture grows at the exact same rate, and not all individuals in the population have the same blood pressure. So we have this variability. So sometimes the observed association or difference that we see is not real. It may be due to chance. So this is the basis of inferential statistics. Can we go to the next slide, please? Next slide. Next slide. Mira, can we go to next slide? Thank you. Now, let's contrast descriptive and inferential statistics. You have discussed, and Dr. Felix did justice to that topic, as always. You have discussed descriptive statistics. So you looked at the measure of central tendencies, you look at measures of variability, the mean, median, mode, the variance, interquartile range, standard deviation, and the rest of them. These measures merely describe and summarize your sample. For example, when you look at the mean, you are just describing. You are telling us on the average, when we take a participant, that person is likely to be in health. The probability is this. Okay. Yeah. Okay. So that's what we are doing. We are looking at the what. Okay. But inferential statistics moves beyond the what to look at so what. So it looks at so what. So it uses sample data to make conclusions, which we call inferences, about a larger population. Okay. And what is interesting is that we use statistics, of course, most of the time wrongly in our daily life. For example, when I was in South Africa, an average South African, when they know that you are from Nigeria, they will say, "Oh, you are from Nigeria. An average Nigerian is a crook." So they are making inference. And I will ask them a question. How many Nigerians have you met? Some of them will say, 50, 200. Then the next question is, what is the population of Nigerians? They will say they don't know. It's over 200 million. Like someone answered the question that we posed at the beginning to say it depends. You see, it depends. So for you to make deductions or inference, you need to have more information. So the more information you need is to say that is our sample, the sample that we take, is it actually representative of the population? How did you even select the sample? You have talked about this. Is it probability, sampling method that you used, or did you use some non-probability sampling method? So it will be impossible for you to make what you call external validity or to generalize on the entire population. So this is what inferential statistics does. It goes beyond just describing what did we see to saying so what for what we have described. I give an example of one of my students. I don't know if he's online. One of my students that I supervised his work for Masters of Public Health. He looked at factors associated with concurrent anemia and stunting using the Rwanda Demographic and Health Survey for 2010, 2014, 2015, and 2019, 2020. So we looked at the trend. Then beyond the trend, we looked at what are these values? What are they telling us? So what? What deductions can we make regarding children less than 2 years in Rwanda? So this is what you call inferential statistics. So the moment you go beyond describing with mean, median, mode, doing your simple tables and graphs that Dr. Felix demonstrated like a magic. So beyond that description, you ask much higher question of so what? What deductions can we make? So you move to the level of bivariate. So you move to bivariate analysis, whereby you are going to cross-tabulate one independent variable against one dependent variable, or a predictor against the outcome, and so on and so forth. Then after that one, you move to the third level, which is multivariate. So whereby you are going to, because bivariate has a problem, and this is something that we are still going to talk about in the presentation. Some researchers would end at cross-tabulation. They end at bivariate analysis to look at whether there is a statistical association between one independent variable and one dependent variable. But the challenge with that one is that there is a variable, a third variable that is called confounder. You have not addressed the issue of a confounder that can distort the association between your independent variable and your dependent variable. So for example, if you say that your study is on diabetes, then you are saying that you want to look at the association between alcohol use and diabetes. There is another variable that affects the association between the two variables, and that is age, because it is established that as people age, so they are, susceptible to diabetes. It's also established in research that the older people are, the more likely they are to consume or use alcohol. So until you isolate the effect of that third variable called confounder, your conclusion will not be valid. So that's what we do in hypothesis testing. So we have so what? So we have described, but the description is not enough. We have moved from data to information, because when we describe our data, we have information. And we know that we make decisions based on information, but it is not enough for us to say, okay, the average is this. So we need to move further to higher levels at bivariate. Then from bivariate, we go to multivariate. So the examples that we are going to talk about, they are hypothesis testing and, of course, p-value and confidence intervals. We are going to expand the discussion as we go along. Let's move to the next slide, please. Next slide. Mira, next slide, please.
The next slide is already on.
Okay. All right. Thank you. Yeah. So now let's look at inferential statistics. So if we have understood the difference between descriptive statistics and inferential statistics, now inferential statistics bridges the gap between data and discovery. It is the process of using sample data to make generalizations, estimates, or predictions about a larger population. So that's what inferential statistics is all about. It's all about making inferences or conclusions, generalizations, estimates, or put differently, using sample data to make generalization about the population from which the sample was drawn. To those of us who cook here online, when you cook a soup and you want to see whether that soup, the pot of soup, is sumptuous and delicious, what do? You take a pinch of that soup and you taste it. Then you say, yummy. This tastes nice. But you did not consume the entire pot of soup. Yet you generalized your findings from that small portion on the entire pot of soup. You are doing inferential statistics if you don't know. So, for reasons of time, we may not have enough time to survey or to deal with the entire population, or for reasons of cost, we may not have money to deal with the entire population, and some other reasons, we do sampling. So we now use sample statistic or the characteristics of a sample to generalize on the entire population from where the sample was selected. So that's what inferential statistics is all about. Why is it important in biomedical research? Inferential statistics is the fundamental mechanism for making evidence-based decisions. So it is very important for us to conduct inferential statistics. So that's why when you submit your thesis to your supervisors who know biostatistics, if you stop at cross-tabulation, they are going to reject your findings. They will tell you to go back and move to the third level and do multivariate analysis, because multivariate analysis is what is going to give you superior evidence for you to make conclusions on your research questions, or for us to see whether your research objective has been achieved or not. Some colleagues have submitted some manuscripts to reputable journals, and the manuscripts were returned to them, and they were advised to consult with a biostatistician. By the way, I always say that a biostatistician is different from a data analyst, because anybody can click and get funny output from data analytical packages. But a biostatistician understands, what is it that I'm doing? Why am I doing it? And how should I do it? So that is the difference. So they approached me for help, and I helped them to move to the third level to now run what you call multivariate analysis. So this is the basis of evidence for decision making in research, even in real life. So for you to make decisions, you need information, and that information must come from evidence that you get from inferential statistics. So that is what is important. That's why we need inferential statistics. So let's go to the next slide. That's why it is important in biomedical research. Let's go to the next slide. Whilst we're still waiting for the next slide. Okay, thank you. It's here. Now, let's look at the core of inferential statistics. In inferential statistics, as I've said, the purpose is to enable you to make decisions about population characteristics. But what are you going to use? You are using sample, because you cannot deal with the entire population. Even if your study is hospital-based, you cannot deal with the entire study population. So you sample. Then, how do you start that process? You start by describing the population using descriptive statistics. Then you develop an hypothesis about differences in characteristics between the population or subpopulation within the same population, so that you can draw conclusions on the association, okay, if the subpopulations are found to differ significantly. So that's what we do in inferential statistics. So inferential statistics has three main branches. One is what you call probability distribution. This is the basis of inferential statistics. If you don't know probability and probability distribution, it will be difficult for you to do inferential statistics. The second one, which is related, is sampling distribution. So, which is also important. So, the probability distribution will describe the likelihood of the outcome from a variable. So, it will be a table that will give you a variable, and it gives you associated probability with that particular observation or frequency. So you have the frequency. In addition to the frequency, you also have the probability of occurrence. Then we have sampling distribution. Sampling distribution bridges the gap between sample and population. Remember what I said, that in inferential statistics, we don't study the entire population. We rely on the sample. So for us to know that the sample estimates are reliable, so we need the sampling distribution. How is the sample characteristics, or what we call sample statistic without S, how are they distributed? So it tells you, it gives you information about their reliability for estimating population parameter. So that's what we do. Now, it is the probability distribution of the sample statistic, like mean, that we calculate from all possible samples of a given sample of a given size. So what this means is that you will take different samples from the population, calculate their mean, and now see how the sample means are distributed. So that's what we do in sampling distribution. And we use this information in hypothesis testing and our other inferential statistics, making conclusions about the population. For example, you talk about the standard error, which is the measure of variability for the sample mean, for example. So this is what we do in sampling distribution. Let's go to the next slide. So in our population, we want to estimate population parameter, rather want to estimate population parameter from the sample statistics. So we want to see how they are distributed, whether they exhibit a particular characteristics of the population or not. So that's what we do in sampling distribution. It is linked to probability distribution. Let's go to the next slide. It's not moving on my own page. Okay, if it is there, let's continue. Okay, so we have estimation and hypothesis testing.
It's not there.
Estimation and hypothesis testing. So that's the third one. Now, estimation, what is that one? What do we mean when we say estimation? So the estimation means that we are going to use sample statistics to estimate population parameter. I assume that we remember what sample statistic mean. For example, sample mean. Sample mean is a sample statistic. What is an example of a population parameter? Population mean. So we want to use sample mean to estimate population parameter. So now, a good estimate will have two characteristics or properties. Number one, it is not biased. That is, systematic error is minimized. Number two, variability from one sample to another sample. A good sample statistic is fairly normally distributed. And the larger your sample size is, the better the stability of the estimate. So that is why we say the bigger the merrier. So Dr. Maker explained and emphasized that even when you use sample size formula to determine minimum acceptable sample size, that's the minimum. It doesn't mean that that is what we expect as the maximum. That's the minimum. Let's say, for example, you use Yamani's formula and you get 386 as your sample size. What it means is that for you to detect whether there is an effect or not, you need minimum of 386 from that population. If eventually you go to the field and you are able to get 1,000 recruited into your study, it's best for you, because the bigger the sample size, the more reliable the estimate that you get from that sample is on the population parameter you are estimating. Put differently, the bigger the sample size, the closer the value, the sample value is to the population parameter value. Let's say what you are looking at is the height. You are looking at the height of people in the city of Kigali, for example. We know that it is impossible for us to measure the height of everyone in Kigali city or in Lagos in Nigeria. So what we do is we take a sample. So when you take a sample, then if you take the random sample, which is representative of the city, then the bigger the sample size, the closer that particular sample mean height will be to the real mean height in Kigali city or in Lagos or whichever city that you are collecting your data from. So that is what we do in estimation. Now, hypothesis testing uses, okay, there's something else I need to mention there. There are two types of estimation, and we are going to see both of them. One is what we call point estimate. That's what we call point estimate. A point estimate gives a single value to represent the estimated population parameter. So that's what we call point estimate. We will see an example very shortly. Then we have what we call interval estimate. Interval estimate is going to create an interval around the sample statistic. So it will tell you, for example, that the height, the average height in that population will lie between 1.65 and 1.80, for example. So it gives you an interval. It doesn't give you a single value. So an interval estimate is better than a point estimate. The reason is because a point estimate does not give us an idea of what we call uncertainty, but an interval estimate gives us an idea of uncertainty. For example, perhaps you have surveyed, you have not included in your survey those who are playing basketball, who are very tall, or you have excluded gymnasts, who of course have shorter height than the average height in the population. So it takes care, an interval estimate takes care of variability within the population. So let's go to the next slide, please. So these are the core of hypothesis testing. So when you do hypothesis testing, you are going to use estimation of p-value, for example, of observing the sample data if the null hypothesis is true. We'll talk more about this. So you estimation and hypothesis testing, they go together. Whether it's a point estimate like your p-value or an interval estimate like your confidence interval. So both of them are used in hypothesis testing to actually to observe whether the sample data, whether the sample statistic, whether it's close to the population parameter that you are trying to estimate. So that's what we do in hypothesis testing. So let's move to the next slide. So now let's look at the procedure, hypothesis testing procedure. Please go back. The procedure, there are 5 steps in conducting hypothesis testing. I'm going to take time on step number 1. This first step is to set up your null and alternative hypothesis. Then you select your alpha or level of significance. So you set up your null hypothesis, you set up your alternative hypothesis, both are related. Then you select your alpha. Your alpha can be 95%, which is what is common in research. It can be 99%, it can be 90%. So 95% is what every researcher would want to use. But sometimes a researcher would need higher precision and say that they want to do 99%. So the second is to select your test statistic. You select your test statistic because it's a test. So there is a statistic that is going to be used that you are going to build around that you are going to use to estimate the population parameter. So for example, if you are dealing with mean, you can set your test statistic around the mean. Then you set up your decision rule. You accept null hypothesis if p-value is less than this. Then you compute your test statistic, you do the calculations, and you draw conclusions, and you summarize your findings. So let's move to the next slide. So this is these are the steps that are involved. There's a whole lot that we do when we look at the steps, but I'm not going to go into details of the test statistics, the decision rules, and the rest of them. But I'm going to emphasize and take a little time on the hypothesis. So let's go to the next slide. So now we want to look at setting up two possibilities. So when you are testing hypothesis, there are two possibilities that are available to you. So you have null hypothesis and you have alternative hypothesis. So these are the two possibilities. So the null hypothesis says there is no effect, there is no difference, there is no relationship, there is no association, null, none. There is no effect. There is no difference between two groups. There is no association between independent variable and dependent variable. Or put differently, exposure is not associated with outcome. So an example will be the new drug is no better than placebo. Alternative hypothesis, it can be written as H subscript O or H subscript 1. It is going to negate the the null hypothesis. It is going to say that there is a difference. It is going to say there is an effect. It is going to say that there is an association. Now, the question is, how do you know which is which? But before we even get into how do you identify your null hypothesis, let me mention this one. Your null hypothesis is usually associated with equality, equal sign. So it will have equal sign. So you would have something like mu, which population mean is equal to an hypothesized value. So it is saying, it will tell you that mean is equal to an hypothesized value, for example. So, or it can say it is less than or equal to, or it can say that it is greater than or equal to. So the alternative hypothesis is what you, the researcher, believes to be true. It is what you believe to be true. It is associated with inequality. So it will give you not equal to, or less than, or greater than. So how do you now distinguish between null and alternative hypothesis? The answer is it depends on your research question. So I'm going to give you some examples and let's pay attention. Let's say your research question is there a difference in patient satisfaction between public and private hospital? I repeat the research question again. Is there a difference in patient satisfaction between public and private hospital? That is our research question. Then our null hypothesis, which says there is no difference, there is no effect, it will say that there is no difference in the average patient satisfaction scores between public and private hospitals. So if you want to use the statistical notation, we're going to say that mu1 is not equal to mu2. So you say H subscript O such that, you write a colon, such that mu1, which represents public hospital, is not equal to mu2, which represents the satisfaction score for private hospital. So that's how we are going to state the null hypothesis. Then the alternative hypothesis for that research question will be there is a difference. There is a difference in the average patient satisfaction score between public and private hospital. So statistically, we are going to say H subscript 1 such that mu1 is not equal to mu2. I hope that one is clear. So that is the null and alternative hypothesis. Now, let me give us another one. Then I want someone to type. I want you to type on the chart. What hypothesis is this one? So pay attention to this. It says the average number of heartbeats per minute is greater than 85. Let's type on the chat box. The average number of heartbeats per minute is greater than 85. Someone says, Festus says null hypothesis. Anyone else? The average number. Okay, Anthony says alternative hypothesis. Cousin says alternative hypothesis. Samuel says alternative hypothesis. Excellent. Thank you. This is an alternative hypothesis. Why is it an alternative hypothesis? Because it is saying it is greater than. It is greater than. I told you that the null hypothesis is associated with equality. It is associated with equality. Equal to, less than or equal to, greater than or equal to. There must be equality. When you write it in statistical form, you should be able to write equal to somewhere there. It can be equal to, it can be less than or equal to, it can be greater than or equal to. That's how you distinguish alternative hypothesis from null hypothesis. So this question is actually an alternative hypothesis. Now, and this, the first one that I gave you, the first question that I gave you that says there is no difference, which is the null, and the alternative says there's a difference, which this is called two-sided. We call it two-sided hypothesis testing. This is very important because many of us in our research, you wonder, why did the reviewer reject my paper? We reject papers because of methodological flaws. You conducted a one-sided hypothesis, but you interpreted two-sided hypothesis. That's a flaw because you run into an error, which we are going to talk about very shortly. Now, so that is an example of a two-sided hypothesis. Let me move on to the other one, or let me give you another example of a two-sided hypothesis. Another example, pay attention. Is the average length of stay for surgical patients in King Faisal Hospital, it's a very popular teaching and referral hospital in Rwanda, different from national standards of 5 days? That is your research question. Is the average length of stay for surgical patients in King Faisal Hospital different from the national standard of 5 days? That's your research question. So how do we formulate our hypothesis from this research question? So we're going to say that the null hypothesis is the average length of stay for surgical patients is equal to 5 days. I repeat again, the null hypothesis will be the average length of stay for surgical patients is equal to 5 days. Alternative hypothesis will be the average length of stay is not equal to 5 days. So you see, equality. Equality is in the null hypothesis when you have two-sided. Equality sign is always there. And even in the very good. Yes. So you will say HO such that mu is equal to 5 days versus H1 such that mu is not equal to, meaning you are going to cross the equality sign, 5 days. So that is another example of a two-sided hypothesis testing. So your research question dictates what will be your null hypothesis and what will be your alternative hypothesis. Then I should also emphasize that when we are testing hypothesis, what you are capable of accepting or rejecting is the null hypothesis. So that is what you are capable of accepting or rejecting. Because some of you, when you are concluding in step 5, you are going to say, we conclude that the alternative hypothesis is true. That is wrong. Because what you are testing is not the alternative hypothesis, because the alternative hypothesis is what you, the researcher, believes. That's what you believe. So what you are testing is your null hypothesis. So you either accept or reject the null hypothesis. Now let's go to the next one, which is one-sided. One-sided hypotheses are also. No, it's not. What I'm saying is not on the slide. I'm just giving you more information. Just remain on Q&A. We will get there, please. I'm giving you more information. This is very important. So one-sided hypothesis can be further subdivided into two. We have one-sided upper tail. If please mute your mic. One-sided upper tail. When your claim or your research question states that the population parameter is more than a specified or hypothesized value, then you have a one-sided upper tail test. I'll repeat myself. Your research question or your claim or your hypothesized value, when it says that the population parameter, mu, for example, which is the population mean, is more than a specified value, then you have a one-sided hypothesis testing. For example, let's see a research question. So you are saying, as the implementation of new patient triage system increased the average waiting time. So that is the question that you are asking. Beyond the recommended 30 minutes, as the implementation of new patient trial system increased the average waiting time beyond the recommended 30 minutes? So that's the research question. So how do we now write one-sided hypothesis from this research question? It is easier. This is what I tell students when I teach hypothesis testing. It is easier for you to start from the alternative because that is your own guess. That is your own belief about what you are testing. So you can start from it to say, because if it is one-sided, it means that the alternative hypothesis will be greater than. The alternative hypothesis will be greater than. So you will say the alternative hypothesis is average patient waiting time is greater than 30 minutes. So that's what you are going to say. H1 such that mu is greater than 30 minutes. So who will tell me what the null hypothesis will be? You can unmute and just respond quickly. Anybody? We fail to reject the null hypothesis.
The mu is not greater than the average waiting time. It's not greater than the.
Thank you, Ayomide. Thank you, Ayomide. Can you mute again?
You are not using that one.
Okay, thank you. Ayomide said the average waiting time is not greater than. Is not greater than in mathematical terms is what? If you want to state that as an inequality, what are you going to write? What are you going to write? Is not greater than, because you are right, it's negating the null hypothesis. But how do we write it in mathematics? You will write less than, right? But remember that a null hypothesis must always have equality sign. So you will say that the average patient waiting time is 30 minutes or less. And if you want to write that one in a statistical notation, you will say HO such that mu is less than or equal to 30 minutes. So there must be equal to there, less than or equal to. So if you have your research question, I advise you to always start from the alternative. The alternative is very easy because that is your own guess about the what you are testing. So now let's look at the second subcategory of one-sided. It is one-sided lower tail. When your claim as a researcher or when your research question is that the population parameter is less than an hypothesized value, then you have a one-sided lower-tailed hypothesis test. So, for example, if we have this research question, all these examples I'm giving you, they are from studies. As the nurse to patient ratio in the ICU dropped below the recommended standard of 1:5. I repeat the research question again. As the nurse to patient ratio in the ICU dropped below the recommended standard of 1:5. So now, if you recall what I said regarding alternative hypothesis specifies your own claim or your research question. It's very easy. So once you look at your research question, just write it in terms of inequality. Then it becomes your alternative hypothesis. Like in this case, we are going to say that HO such that mu is not equal to, mu is less than 5, such that mu is less than 5. Then the null hypothesis will be HO such that mu is greater than or equal to 5. So these are the possibilities when it comes to testing hypothesis. Now let's look at the Q&A. Let's look at the Q&A. In the charts, you can type your null hypothesis and your alternative hypothesis, your own, just any research question that you may have dealt with before. So let's have some response to that before we move on to the next slide. Write your null hypothesis and your alternative hypothesis for your particular research question. I repeat myself again. The hypothesis depends on the research question that you have asked. Okay, and the alternative hypothesis is what reflects your own your understanding of that test, what you claim, or your research question. It mimics your research question. So let's have, can I see some response from the previous studies that you have done, or you can think of a research question now and type what will be your null hypothesis and what will be your alternative hypothesis. Can we do that quickly? I can't see any. Okay, we have Benvenue Concord. Oh, it's gone. If we let's see what is in the chat. I want to see what some people have written. Someone says, Concord said, if we reject or accept null hypothesis, does it mean alternative hypothesis is true, or we need to test it too? Okay. Like I said, we do not test alternative hypothesis. What we test. Can you mute?
No.
We do not test alternative hypothesis. We test the null hypothesis. That's what we test. Now, does it mean that alternative hypothesis is true? Probably. Probably it is true. You see, what we do in conclusion is that the sample evidence is insufficient to accept the null hypothesis. So we try to be careful in framing our conclusions, depending again on the study design. This you have discussed. The study design determines whether. Can you please mute? Okay, let's look at. Okay, thank you. Let's look at. Please mute. I think I've answered that question. So we're not testing alternative hypothesis, but it is probably true. So you will say the alternative hypothesis is probably true. So you have to put the issue or the concept of probability there. The alternative hypothesis is probably true. Now let's look at what Festus wrote. High phosphorus use efficiency is associated with root morphological traits in sorghum genotypes. So that is the hypothesized statement. So what will be the null hypothesis? So he's saying it is associated. He's saying there is an association. That's your null hypothesis. So what will be the alternative hypothesis? The alternative hypothesis will be high phosphorus use efficiency is not associated to with morphological traits in sorghum genotype. That's a two-sided hypothesis that you are testing. Let's look at Protegene. Protegene says the quality of paracetamol tablet available on Rwanda market complies with standards. So if it complies with the standard, you can write equal to there. It means that is your null hypothesis. So the alternative will be it does not comply with the standard. So now let's see Ibrahim, then we move. Suleiman Ibrahim says his own alternative hypothesis is that there is significant difference in renal parameters between MGUS and multiple myeloma. Absolutely correct. So this is wonderful. This is fantastic. We can give ourselves a round of applause. All those that have read their hypotheses, they are correct. Now let's move on to the next one. Let's move on to the next slide because of time. Let's move on to the next slide. Thank you for your response. Now, in the next slide, we are looking at another important concept in hypothesis testing. If we don't understand that concept, we cannot reach meaningful conclusion. Alexis says, is higher flow oxygen delivery better than standard flow oxygen? And he states the hypothesis as HO such that you don't write comma, you put colon there. You can correct yourself, Abimana. Correct yourself. You say HO such that you put a colon. HFO is equal to SFO. Then H subscript 1 such that HFO is greater than SFO. There are two things that we need to correct in your hypothesis. The research question is okay. Number one, we start stating a hypothesis by the null hypothesis. You will start with H subscript O first. That's number one. Number two, your hypothesis is not matching. The alternative hypothesis is not matching with your null hypothesis. Can someone see? If you can look and you can see, because not everybody that can look can see. If you can look and you can see, can you look at what Abinamana typed? and tell me what is wrong with that alternative hypothesis. The null hypothesis and the alternative hypothesis. Let's look at his research question. He says, is higher, thank you, we will get to p-value now. Is higher flow oxygen delivery better? Better means what? Greater than, right? Are we together? Better means greater than, which means that your alternative hypothesis is correct. But your null hypothesis says is equal to. Remember, this is when you have greater than. This is a one-sided hypothesis testing. I took a little bit of time to explain one-sided hypothesis testing and two-sided hypothesis testing. So one-sided hypothesis testing, when it is saying greater than, like in your case, it is upper tail. This is upper tail. Then you are going to change that inequality for the null hypothesis to say that HFO is less than or equal to. Confidence says, I don't quite understand the one-sided hypothesis. Okay, let me repeat myself again. There are two cases of one-sided hypothesis. Let's use Abimana's case because it is displayed on the screen. So we use Abimana's case, which says HO such that HFO is less than or equal to SFO. So that is HO. H1 will say, it will negate it. It will say HFO is greater than SFO. Okay. Confidence, is that clear? Then you have another possibility, which is one-sided lower tail. So if Abimana's question is lower oxygen HFO delivery better than standard flow oxygen? Lower. You are saying lower, which means your alternative hypothesis will be H1 such that HFO is less than SFO. Then your alternative hypothesis will be your null hypothesis will be HFO is greater than or equal to SFO. So that's how we state the hypothesis. Okay, very good. Because of time, let's continue. Thank you so much to all those who give us their null and alternative hypothesis. That's wonderful. Now, if we are done with hypothesis, let's look at p-value. What exactly is p-value? You must realize that this is the most misunderstood number in science. So the simple definition of a p-value is that it is the probability that your observed result or more extreme result if null hypothesis is true. So it measures the probability that your observed result is not due to chance. So that is what the p-value measures. So it tells you whether the association, whether the difference, whether the effect is actually meaningful or whether it is due to chance. So that is what your p-value is measuring. So now let's look at what it is not. Your p-value is not the probability that the null hypothesis is true. It doesn't tell you that the null hypothesis is true. But what it is saying is that if the null hypothesis is true, that condition must be there. If the null hypothesis is true, then the observed association is statistically significant. That is, it is not due to chance. But it doesn't tell you that p-value is, that your null hypothesis is true. It doesn't tell you that. It is also not the probability that your findings are false. It is a measure of the size, or it is not a measure of the size or importance of an effect. So your p-value, which is a point estimate, is not a measure of effect or size of an association. It merely tells you that there is a statistical significance association, there is a difference. So that is what is done. So the p-value is conditional on the null being true. So the condition is that the null hypothesis must be true. Then if the null hypothesis is true, it can now be interpreted like there is a difference, there's an association, or there is no association and there is no effect depending on what you get. So it doesn't tell you the truth about the null hypothesis itself. The null hypothesis. It doesn't tell you anything about it. It just says that if your null hypothesis is true, that is, there is no difference, there is no association, there is no, so so it's conditioned on the null hypothesis. I emphasize again that the null hypothesis is what we are capable of testing. That is what we are capable of testing. We cannot test the alternative hypothesis. So we test the null hypothesis. So if the null hypothesis is true, we can now interpret our p-value. So that is what our p-value is all about. So we have to be careful about the use of p-value, because there is a whole lot of misuse of p-value and misinterpretation of p-value in research. And for those who are doing thesis also, we see some funny things that they do with p-value. We'll talk about that. So let's go to the next slide. Let's go to the next slide. So it is not a measure of effect, as we said. So the next slide is looking at the alpha, which I've talked about, the alpha level, the alpha threshold, the alpha. So your alpha, okay. Are we there? Okay, thank you. So your alpha is also called level of significance. It is called level of significance. Now, for hypothesis testing that is two-sided, your alpha will be distributed on both tails. That is why you are going to shade the tails of asymptotic. Asymptotic means it will never touch the x-axis. So you are going to shade the tails, the upper tail and the lower tail, and distribute your alpha or level of significance there. So it means if you are using 95% confidence interval, your alpha will be 5% due to what we call probability density function. I told you that hypothesis testing rests on the foundation of probability distribution. So probability density function says that the entire function is equal to 1. So if your confidence interval is 95% or 0.95, then the shaded regions will be alpha over 2 or 0.05 divided by 2, which will give you 0.025. So that is your level of significance. It gives you the critical region. It's very important. That's why it's called the threshold. It gives you the boundary of what constitutes acceptance of the null hypothesis or the rejection of the null hypothesis. So that is your alpha. So your alpha is closely related to your confidence level. If your confidence level is 95%, then your alpha will be 5%. If your confidence level is 99%, then your alpha will be 1%. If your confidence level is 90%, then your alpha will be 10%, and so on and so forth. So the decision rule is that if your p-value is less than 0.05, we reject the null hypothesis. If your p-value is less than 0.05, we reject the null hypothesis. The reason is because the test statistics that you have calculated, for example, the sample mean, the test statistics that you have calculated from the sample mean for the hypothesis that you are testing will fall within the rejection region, or what you call the critical region. So that is that. So if p-value is greater than 0.05, so we will fail to reject the null hypothesis. There is no strong evidence to accept the null hypothesis. And I want you to pay attention again to the person who asked the question, can we test alternative hypothesis? I repeat myself, no, we don't test alternative hypothesis. The way we reach conclusion will tell you what the conclusion is. So you are going to say that you fail to reject the null hypothesis. You are not going to say we accept the alternative hypothesis. So that's the way we frame it. But the question will be, why do we use 5% or 10% depending on the confidence level? The answer is it is arbitrary, but it is universally acceptable in research that we set our confidence level at 5%. But sometimes a researcher would want a greater precision and will set something like 1%. And sometimes a researcher would want a lower precision and will set an alpha level of 10%. Now, it balances between being too strict and missing the real effect, and being too loose, claiming false effects. So to say that there's an association when there's no association. So we talk about type 1 error and type 2 error, which we are going to talk more about there. So this is the alpha when you are testing hypothesis. Your alpha is conventionally, or what is common, even all statistical application packages, they are using 5% as your alpha threshold, which is associated with 95% confidence interval. So now let's go to the next one, confidence interval. Let's move to the next slide. We look at the confidence interval. Okay, we have some question here. Can alpha be 0? Can alpha be 0? The answer is no. Alice, alpha cannot be 0. Because let me cast your mind back to what I mentioned at the beginning. Probability is the foundation of inferential statistics. If the probability, okay, you know, one of the properties of probability is that it takes value between what? It takes value between 0 and 1. 0 and 1 are not inclusive when you have probability. If you calculate probability and it gives you 1, that is not probability, that is certainty. That gives you certainty. For example, if we say, what is the probability that a student chosen at random from biostatistics class studies biostatistics, of course, the probability will be 1. If all of them are in biostatistics class, then they are all doing biostatistics. So the probability will be 1. So then that is certainty, not probability again. If you calculate probability and it gives you 0, then it means impossibility. It means impossible. It's not possible. So it cannot be 0. Another question from Proctegin says, how can we calculate p-value? You want to calculate? I'm trying to avoid calculations. You want to bring back calculations. Okay, so we can calculate p-value, but the reason why I don't even bother in this webinar about calculations is because you will be using your statistical application packages to do the analysis. It's not that you are going to use pen and paper. So that is on that. Let's go to confidence interval. Our time is fast spent. What is a confidence interval? Remember what I said regarding estimation. There are 2 types of estimates or estimation. There is a point estimation. An example is your p-value. Your p-value is a point estimation. It gives you a single value. Your confidence interval is an interval estimation. It is a better estimation because it gives you information regarding uncertainty that exists within the population. So a confidence interval is more informative than your p-value alone, because if you have p-value alone in your bivariate analysis, if p-value alone is what you have, or if you report only p-value for your multivariate analysis without confidence interval, we do not have much information about the association. We can see that there is statistical association, but we don't know how precise that estimate is. So the confidence interval will give us a measure of precision of that estimate. So it's a better estimate than the point estimate p-value. Now, sometimes you have a result that shows a very wide confidence interval. Even if the p-value is statistically significant, your estimate is not precise. So the measure of effect is not precise. So it's not reliable, put differently. So that is why we prefer confidence interval. And if you recall, last month, Dr. Felix mentioned that there are some people that now talks about confidence interval. They want to do away with the p-value. I do not belong to that group. You present both. Although, if you present confidence interval alone, we will be able to say whether there is a significant statistical association or not. But if we present p-value alone, we cannot say anything about the precision of that measure of association or that measure of effect. So that's why confidence interval gives us more information. Now, let's look at sample interpretation for confidence interval. If we were to repeat this exactly 100 times, we would expect the calculated confidence interval to contain the true population value in 95 of those trials or studies. Let me give us an example here so that we understand what we are saying. Let's say that in a study of Kigali residents, an average height that is documented in government statistics, the average height for a Kigali resident is 1.76 meters. So that is the average height that is recorded for an average person in Kigali city. Then we took a random sample of Kigali city residents. We construct, or we do what we call estimation around that sample mean, because we are going to get the sample mean. Then we will now construct confidence interval around the sample mean. Let's say it gives us 1.68 to 1.82. What this means is that in 100 time that we are going to take such samples from Kigali city, we will be 95% confident that we are going to get 1.76 in that population. So that is what we are measuring with confidence interval. So let's look at interpreting confidence interval. Let's go to the next slide to interpret confidence interval. Confidence interval, as we said, is what is a range. It gives you a range of values within which the true population parameter lies. Like the example I gave, the true population parameter is 1.76, and the confidence interval that we built is 1.68 to 1.82. So you see that the true population parameter falls within this range. Let me tell you something that I've noticed in reviews. Dan says, how do we know that the confidence interval is wide? Very good question. Let's look at the example that I gave. Let's say your calculated height from samples that you collected is 1.65. That is the X bar that you calculated for the height among the sample that you selected from Kigali city. Then you build the confidence interval. So you have your z-score, which is equal to X minus X bar divided by your population standard deviation, or something like that. So now, when you do this one, is going to give you, let's say it gives you something like, 1.02, 20.59. You see that confidence interval? It is saying that the true population height, the true average population height will lie between 1.02 meters and 20.59 meters. Some of you don't pay attention to confidence interval. Wide confidence interval shows that there is lack of precision in your data. It means your sample is not representative enough of the population from which it was drawn. All right. So, this is what we observe when we review manuscripts. When they send papers to us and we look at, I give an example. I sat in a panel here in Kigali, and the student presented his findings, a master of public health students, and all his p-values, all of them were less than 0.001, all of them. But when I looked at the confidence interval, it is impossible for some of the p-values to be significant. And I'll talk more about that. So you may have a very wide confidence interval, and sometimes when you run multivariate analysis, there are two problems you can run into if you have fewer cases per cell. You can have sparse data problem, which will lead to overfitting. Okay, so when this happens, your confidence interval may even give you error. It may not converge. The data may not converge when you run the model. So it may give you error, or you may have very wide confidence interval. So instead of 1.02 to 20.59, if we have something like 1.62 to 1.74, that one is narrow. So the narrower your confidence interval, the more precise your sample estimate is. It means that your sample statistic that you are using, in this case, the sample height, the sample average height, it means it is closer to the true population height. So when you have narrow confidence interval, your estimated sample average or sample statistic is closer to your true population parameter it is estimating. So that is why we need to be careful about wide confidence interval. So now, let's look at interpreting. Let's look at it. Example. So you go from a number to a story. We find a mean difference in blood pressure of -5 mm of mercury between drug and placebo with a 95% confidence interval of -9 to -1. So how do we translate this one? How do we interpret it? We will interpret it by saying that we're going to say that we are 95% confident that the true mean difference in blood pressure for the population from where the sample was drawn lies between a drop of 9 mm of mercury, a drop of 1 millimeter of mercury. So now the beauty of confidence interval is that you can see the magnitude and significance at once. You can see the effect and you can see the statistical significance. It can give you an idea of the significance of the value. Now, here you can see that the entire interval is below 0. So, which means that we are confident that the drug lowers blood pressure, and we can also see the effect. We can see the effect that it ranges from -1 to as large as -9. So this is a very huge effect. So we'll talk a little about that also, but let me hear from you. I've been doing the talking. Let's do this one and interpret together. Let's go to the next slide and interpret confidence interval together. So you pay attention. Confidence interval that crosses 0, that includes 0, can never give you a significant p-value. I will repeat myself. Confidence interval that includes 0 can never give you significant p-value. So this is how we catch those who are doctoring their data, because they will present like the example I gave you. The student gave all the p-value, p less than 0.001, all of them. But when I looked at the confidence interval, let me give you an example of his. Thank you very much. We will go there. When I look at his confidence interval, one of them ranged from -2.2 to +20.5. It is not possible, because when you draw your number line, if you go back to primary school, when you draw your number line, -2.2 includes 0. When you move up to 20.5, there are two problems with his data. Number one, he lied with p-value. That p-value can never be significant because it includes 0. When confidence interval includes or incorporates 0, it can never have significant association. Then number 2 is confidence interval is wide, negative 2.2 to positive 20.5. So that is that. Now let's do this mini case together. Let's interpret together and see. So it's a clinical trial results. So we're comparing new drug to standard therapy. What is the outcome? Tumor size reduction in percentage. Result, mean difference is equal to 8%. 95% confidence interval gives us negative 2% up to 18%. P-value is equal to 0.110. What does this tell us? Is the new drug effective? Can the confidence interval and p-value, let's discuss the confidence interval and the p-value. You can on the chart, please. Let's do that in few seconds because of time. Tell us something about the confidence interval and the p-value. I'm waiting for your response on the chart. Okay. Vedaste says the new drug is not effective. The new drug is not effective. Okay. Because the p-value is greater than, it is greater than what? 0.05. Then Dan Moramsi says confidence interval as a 0. That is true, because if you look at the result, it ranges from negative 2% up to positive 18%. So this includes 0. Thank you very much. I like this. You understand what we are doing. Let's move on to the next slide. Because of time. So when the confidence interval includes 0, your p-value can never be significant. If your p-value is significant, is either you have deliberately lied with your data or there was a mistake when you are writing your p-value. But if it was a mistake, it's still on you. The onus is on you to check what you have put into your paper. Now, let's go to navigating the pitfalls. This is also very important. Let's look at the pitfalls. Why we have good concepts, but they may go bad. So let's look at that. How can we trust your conclusions? There are so many papers. That have been retracted after many years of publications because of some of these methodological issues which border on biostatistics. Some conclusions are not supported by the data. So let's look at what we need to pay attention to. Now, the tools that you are using may be sound, but they may have been misapplied or misinterpreted. So we need to understand the common pitfalls, and we look at the best way that we can address these pitfalls to avoid them, and of course, to critique other people's research. When we say critique, we're not just finding fault, we are praising. When we conduct research, we appraise evidence to say that, okay, this study finds this. Nevertheless, when we look at the sample size is small and may not actually support or justify the conclusion reached. So let's look at some real-world examples from the literature. So that's, we move to the next slide. So I've brought some examples from the literature for us to see what we need to pay attention to in our own research. And of course, when we are doing literature review, either for discussion or we are writing a review paper or we are just critiquing evidence, you know what to look for. So let's look at the next slide. The first one we are going to look at there is what a p-value is not. We've talked about this, but I'm bringing evidence from published papers. So what a p-value is not. So let's look at that. Now, what is the mistake in this one? I'm quoting from that paper. We found a p-value of 0.02, meaning there is only 2% chance that our result is due to chance. The null is true. What can you say about this? So the reality is that the fundamental, it is misrepresented. It is misinterpreted. Because when you say your p-value is 0.02, it means that this is less than 0.05, right? That is correct. I agree with them. 0.02 is less than 0.05. So which means there is that statistical significance. But to claim that our result is due to chance, the null is true, is incorrect. I hope you get it. You cannot claim, because as I said earlier on, the p-value will only give you a conditional statement. It will say that there is an association on the condition that the null hypothesis is true, but it will not tell you whether the null is true or not. So the p-value assumes that the null hypothesis is true, but it cannot tell the probability that the null hypothesis is true. So how do you avoid this pitfall in your own paper? You stick to the former definition. Use this language: evidence against the null. Or you're saying that our finding is incompatible with the null, or similar statements like that. Or you say the sample evidence is insufficient to accept the null hypothesis. So this is what you can do to avoid this kind of pitfall. So you cannot claim that p-value is testing the truthfulness or otherwise of your null hypothesis. Let's move to the next slide, please. So that is how you can avoid that pitfall. Avoid interpreting p-value. Okay, okay, very good. There is a question here. Dan is asking a question. Does this principle hold on outcomes for proportions? Dan, thank you very much for bringing this question. Because of time, there are so many things we may not be able to talk about unless there are questions like this. When we are testing hypotheses, it depends on the nature of your research question. What research question are you asking? If you ask a research question that gives you a continuous value, like some examples that I've given you earlier on. I've given you some examples of research questions that are asking about mean, what do you call it, satisfaction score. So if your question will give you variables that are continuous in nature, then you are going to test your hypothesis on the mean. You will test the hypothesis on the mean. But if your research question is framed in such a way that you can only get categorical variables, if you are going to get categorical variables, then you will test proportions. Yes, the answer is the principle holds even for proportions. But the test statistic is not the same for when you are testing for mean or when you are testing for proportion. Thank you, Dan, for bringing that. Now, let's look at the second pitfall. Let's look at the second pitfall. The second pitfall is that you can fall into the significant trap. There is a difference between statistical significance and what you call practical significance. There's a difference between statistical significance and practical significance. And researchers in the house and some of my senior colleagues, professors, you know better that when we conduct research, we also trying to see what is the contribution of this research, or what is the significance of this research, who is going to benefit from this research, how are they going to benefit from this research. Okay, so sometimes you can find statistical association, but in terms of practice it is meaningless. For example, you do a study in your clinical practice, maybe on surgical procedure, there is statistical significant association, but it will not change your clinical practice. You that you conducted the study will not change your clinical practice with regard to surgical procedure based on that finding. Then all you find is statistical association. There is no practical significance. So let's see the mistake. Focusing only on p-value to declare an important finding is not enough. So the reality is that with large samples, trivial effects can be significant. With small samples, large effects can be non-significant. So how do you solve this problem of significance trap? Always report effect sizes and confidence interval. Always report your effect sizes. There are so many effect sizes, but I'll just give you 2 or 3 examples. Now, you can use odds ratio, for example. Odds ratio is an effect size. So you can use it to report odds of an event in 2 groups. So if odds ratio gives you 1, for example, there is no effect. If odds ratio is greater than 1, there is an increased odds. If odds ratio is less than 1, then there is a decreased odds. So another example of effect is Pearson's R. Pearson's R can be used to determine the effect, linear relationship between 2 variables. So how do you interpret Pearson's R? If your R is equal to 0.1, there is a small effect. If your R is 0.3, there is medium effect. If R is 0.5 or more, there is a large effect. So there are other measures of effect. There is OND, there is hazard ratio. Can you please mute? There is hazard ratio and the rest of them. So always report effect size around, and also construct confidence intervals around your effect size. So is your effect size meaningful in the real world? So the effect size answers a very simple question. Instead of saying statistical significance, it answers a question: how big is the difference? So you are saying there is a statistical difference. How big is this difference? Okay, how big is the difference? For example, a new drug is having just about 1 millimeter of mercury difference in blood pressure. Is that a big event? Even though the p-value is saying significant, but that's a small effect. But if it is saying that the new drug reduces blood pressure by 15 millimeter of mercury, then we know that's a big effect. So effect size gives you the size of that particular difference or association. Okay, so that is that one. Now, always report. Let's go to the next slide. Always report effect size and don't limit yourself to p-value or significant values only. And this is also important for those who are stopping at bivariates, as I alluded earlier on. That if you stop at bivariate, you will not be able to see the measures of effect. Of course, there are measures of effect you can also calculate for bivariate, but because of confounding that we've talked about, it is not as robust as when you report the measures of effect that are associated with multivariate analysis, like your risk ratio, like your odds ratio, like your co-ND, and so on and so forth. So let's move to the next slide and look at another pitfall that we need to avoid. So another pitfall we need to avoid. Next slide. Another pitfall is multiple testing. Next slide. Multiple testing. So some of you would want to look again, you want to look again, you want to look again. You are just looking for positive, sorry, you are looking for significant p-value. So you test and test and test and test again and again. But there is always a price to pay. Emmanuel, I don't get your question. You typed a question. I don't get it. Of what of co-ND? Co-ND is a measure of effect. It measures differences between two means. Co-ND measures the difference between two means. So if co-ND is 0.2, that effect is small. If it is 0.5, then it is a medium effect. If it is 0.8, then you have a large effect. So it's a measure of effect. Okay. Let's move to the next slide. Welcome, Emmanuel. Next slide, we are looking at another pitfall, which is the price you pay when you are testing again. And we have mentioned before in previous presentation, and Dr. Felix also emphasized this. It is not for you to tamper with the result. There must be scientific integrity. You must have integrity to report what you found. Don't change the data because you want, don't change the result because you want a significant p-value. You report your findings. Thank you. So multiple testing problem, the price of looking again. Now let's look at the mistake. Running 20 tests at alpha or significant level 0.05 and being surprised when one is significant. Out of the 20 tests, only one is significant. So what is the reality? The reality is that by chance you expect one false positive for every 20 tests. So that is the reality. So the more you test, the higher the chance of getting false positive. Okay, so your error rate is 100%, not 5%. So how do you solve this problem? You solve this problem by planning ahead of time, and you use what we call correction methods for multiple comparison. For example, when you run your ANOVA, analysis of variance, and you are comparing different groups. You have multiple groups. You are comparing multiple groups to see where lies the difference. because F statistics is going to tell you that there is a significant difference, but it will not tell you in which groups or combinations do we have the difference. So you run multiple comparison to say, let's compare these against that. Let's compare this against that. So the more you test, the higher your chance of getting false positive. So what you do is you correct. There are statistical principles for correcting for multiple comparison. One of them is born for any, but there are so many of them. If you are familiar with statistical application packages like SPSS, you find all of them listed there, depending on what we are doing. So that is the price to pay. Avoid unnecessary tests. We're not saying don't do multiple comparison, but if a test is not important, don't run it, because the more you run the test, the higher your chance of getting false positive. Let's go to the next slide. Next pitfall. Next slide, please. Next slide shows what we have mentioned even when we introduced this sensitization program. It is called p-hacking. It's called p-hacking. Trying different analysis until you get a p-value that is less than 0.05. So this is not good. So it is not good. So it's another pitfall that you need to avoid. So what is the mistake? The mistake is you are trying different analysis until you will get a p value that is less than 0.05. For example, when you are running a multivariate analysis, conceptually there are some variables that are supposed to be in your model, but because you desire to get a positive association, or you desire to get a significant p-value, you deliberately removed some variables. So that is not good. The reality is the undisclosed flexibility makes p-value meaningless. It is a major contributor to a replication crisis. So this is one of the reasons whereby you will say, I replicated a study done in Nigeria, here in Kigali. Why did I not get a positive value as the Nigerian researchers? The reason may be that the Nigerian researcher have tried different analysis until they got, I'm not accusing anybody, I'm just giving an hypothetical example. So it may be that they have done different analysis until they got a p-value that is less than 0.05. So how do you solve this problem? You can solve the problem through pre-registration. For some study designs, some studies must be registered. Like if you are doing clinical trial, it has to be registered. It is a must. And again, you have to be transparent. Research integrity is very important. You must have integrity. Report what you found, not what you think should be found. Report all analysis. Don't ignore some analysis because they do not have a positive p-value. So don't just report the good one. Let's move to the next slide. This is something that we need to work on, because some researchers are fond of reporting only significant p-values. You may be surprised that some of your non-significant results may also contribute. They may provide baseline information for other researchers to explore deeper. Maybe they get a better evidence. So let's go to the next one. The next slide looks at something I expect you to do. Next slide. Next slide, please. So there I want you to do something. I created an abstract conclusion, and I want you to identify as many pitfalls as you can from that conclusion. Okay, listen, we measured 50 variables. Listen to that. We measured 50 variables. After adjusting for outliers and controlling for age and sex, we found a significant association between cucumber consumption and mood. Next slide. It says we measured 50 variables. 50 variables. After adjusting for outliers and controlling for sex and age, we found a significant association between cucumber consumption and mood. Next slide. So what do you see there? What pitfalls can you identify there? We measured 50 variables. After adjusting for outliers and controlling for age and sex, we found a significant association between cucumber consumption and mood. Let's type on the chat box. You tell me what pitfalls you can see from that. Thank you. We measured 50 variables. After adjusting for outliers and controlling for age and sex, we found significant association between cucumber consumption and mood. P is equal to 0.04. Mahmoud is saying, it's gone. Area is okay. So Florence is saying focusing only on P value to give conclusion. That is correct. Then Dan is saying the effect is not reported. That is correct. Dr. Gladys says we can't measure 50 variables in one study. While it is possible, we can measure as many variables as possible. It depends on the nature of the study that we're doing. But can we put 50 variables at once in a model? The answer is no. We cannot put that number of variables. Okay, what other pitfall can you find? Did you see p-hacking? Did you see multiple testing? So these people, they have conducted many tests before they arrived at P is equal to 0.04. So this is a false positive. There is no, we cannot rely on this finding. And all your submissions are also true. Thank you very much. Can we move to the next slide? Move to the next slide. So next slide we're looking at, which is the last aspect of our, I'm sorry, we have taken much of our time. We move to choosing the right test. This is also very important, choosing the right test. How do we choose the right test of hypothesis? How do we choose the right test? So that's what we are moving on to. Now, the choice depends primarily on your research question. It depends on your research question. Are you comparing groups or are you finding association or relationship? Are you comparing groups? Are you saying that there is no difference between males and females? Or are you saying that there is no association between alcohol use and diabetes. So it depends on the type of research question that you ask. Number two, it also depends on the type of data. We have discussed this before. Your variables can be quantitative variable and your variable can be qualitative variable. You recall that your quantitative variable can be associated with numeric data, and the numeric data can be measured on interval or ratio scale. And your qualitative variable can be associated with categorical data, which can be associated or related with nominal scale or ordinal scale. We have explained this one. Dr. Felix explained and he gave examples. So these are the two. Let's move to the next slide. These are the two important considerations. What is your research question? So the way you frame your research question determines the choice of test that you are going to use. Also remember that in what we discussed before, when we discussed study design, your study design is a plan of how you are going to go about the entire study. The study design that you use determines what sort of questions, research questions you are going to be asking. Okay, if you are using cross-sectional design, for example, you cannot be asking questions about causation because of lack of temporality, because exposure and outcome will be collected at the same time. So we don't know which one comes first, whether it is egg that comes before chicken or chicken before eggs. So if you conducted experiments like clinical trials, then you can be talking about causation. You can be talking about causation, or you can imply causation. So now let's move to the next slide. Let's move to the next slide and see the type of data. So if you have categorical data, the values that you have there represent categories. They are codes. They are not numeric. They are codes. Very good. Thank you. The values represent category. For example, if you say male is equal to 1, female is equal to 2, it doesn't mean that males are greater or better or higher in whatever you are measuring than, females are greater or higher or better than males. It doesn't mean that. That 1 and 2 those are codes that you use to represent them. Example, treatment group. You can say you have drug versus placebo. Disease theta, you have yes, no. For example, you say diabetic, yes, no. So that is categorical. Now, continuous, quantitative, numerical values that can be measured. For example, blood pressure, tumor size, age, concentration. You can measure satisfaction level, and so many things. Let's move to the next slide. So that is on the data type. So you look at the data type determines in part the choice of statistical test. So some papers are rejected by reviewers on account of a wrong choice of statistical test. You ask a question, you ask a research question that gives you categorical variables, both independent and dependent, or predictors and outcome. They are categorical. But when you are testing your hypothesis, you are testing hypotheses that require different data types. So these are what happens. Now let's look at the case study. The case study that we're looking at is looking at comparing two means t-test. The research question is the mean cholesterol level in patient taking drug A, is the mean cholesterol level different in patient taking drug A versus drug B? That is the research question. Is it different? So what are you testing here? Let's look at the two questions. So we say it depends on the research question. Are you measuring differences or are you measuring association? Are you comparing groups or are you finding association? What are we doing here? So the outcome is cholesterol level, okay, which is the data type for cholesterol level is continuous. That's a continuous data type. And the predictor, your predictor or your independent variable is the drug type, which is categorical. So we have two groups. So when you have two groups and your outcome variable is measured on a continuous scale, you are going to use t-test. You will use t-test. If they are measured at 3 or more levels, t-test cannot handle that. It will iterate forever. If they are measured at 3 or more levels, you need to move on to analysis of variance. ANOVA is going to assist you to do that. So the appropriate test in this one is independent t-test because you have two unrelated or independent groups. If you have two related groups, then it's something that you are going to do. For example, if you gave your students tests before the module, then you give them the same test after they have learned biostatistics module. Same test, nothing changes. Same people, just one group of people, but you gave them tests at different times. So we call that one paired comparison group. So you use paired t-test. You use paired t-test when you have the same set of people, but you have different data that you are using. Let's move on, okay, to ANOVA. Let's look at ANOVA. Now, for ANOVA, the research question will be, because we are comparing 3 or more means. We are comparing 3 or more means for 3 or more groups. The research question will be, is there a difference in average crop yield across 4 different fertilizer types? So you see, how many groups do we have here? There are 4 groups. So you cannot use t-test when you have 4 groups. T-test is going to work when your group is limited to 2. So when you have 2 or more, you use ANOVA. ANOVA can be one way, ANOVA can be two way. Now, the outcome is crop yield, which is continuous, and the predictor is fertilizer type. So it is categorical. We have 4 groups. Let's move to the next slide. So when you are comparing two, you use t-test. When you are comparing 3, you use ANOVA. So you see that the choice of your test depends on the research question that you asked and the nature of dependent and independent variable. Now, we move to the next one. We are looking at categorical outcomes. Categorical outcomes, categorical independent variables or predictors. The research question is smoking status, smoker versus non-smoker, associated with with developing lung cancer? Is smoking status, smoker or non-smoker, associated with developing lung cancer? So you see that here, both variables are categorical. Your research question suggests that your variables are both categorical. So when both variables are categorical you use your chi-square test. The chi-square test is appropriate. Let's move to the next one. We're almost there. We're sorry for taking your time. Let's move to the next one. So the next one, we're looking at correlation. Correlation, you are finding association. But before they display this slide, let me say something about correlation. First, people misuse the word or the term correlation when they want to say there's an association. They will say we correlated age against, or you say we correlated smoking against lung cancer. You don't use that term in that way. It is wrong, because correlation is applicable when both variables are actually continuous in nature. And what you are finding is not only association, but you also want to find the strength of the association. Correlation can give you even the strength of the association. Otherwise, if you want to limit yourself to finding association only, you can run a regression model. It will give you the measure of association. So let's look at the question. If your research question is, as age increases, does blood pressure also increase? What are the variables there? Age is a predictor. It's actually a confounder. Then you have blood pressure. Both variables are continuous. So when you have continuous variables, the appropriate test will be Pearson correlation. Pearson correlation. So that's what you are going to report. Let's move on to the next. Okay, this is the last slide that we have. So we can see there are other tests, but because of time, we don't have that. Someone's Ayo Mikposi says, please help me with the screenshot of the first case study here on WhatsApp. Okay, they are going to address that one. Now, we've come to the end of the presentation, so we look at our summary and key takeaways. The key takeaways that we want you to have from this presentation today is that a p-value measures compatibility with the null hypothesis. It does not measure its truth. You can't say because your p-value is significant, then your null hypothesis, your p-value is not significant, then your null hypothesis is true. Number two, a confidence interval is often more informative than a p-value. And the reason is because the confidence interval will, in addition, gives you a measure of effect. It will show this magnitude, the size of the effect, not just the association. It will give you the association, it will give you the effect. And again, a confidence interval will give you an idea of the precision or the reliability of the measure of association. So number three, always choose your statistical test based on your research question and your variable type. You cannot have a research question that suggests both are categorical and you are saying that you are running ANOVA. ANOVA is not going to work on categorical variables, although statistical package will give you results because you have coded your age as numeric. So it will give you some results, but the result is meaningless. So number four, statistical significance is not the same as practical significance. Always use measure of effects to make decisions in terms of practical significance. So you ask yourself this question: what does this finding mean for me in my practice? Am I going to change my clinical practice based on this finding? If the answer is yes, then your finding is not only statistically significant, it is also clinically significant. If you ask a question, will this finding contribute to policy change? If the answer is yes, policymakers are going to smile upon reading your research findings, especially if you provided policy brief, then there is practical significance. Beware of multiple testing, p-hacking, misinterpretation, and significant trap. Pre-registration and transparency are your best allies against bias. So with this, we've come to the end of our presentation. I thank you very much for your participation and your patience, because I've taken much of your time. I welcome questions. Questions? Thank you. Yes, if there are no questions, so we have come to the end of the presentation. Prof from Lautech, thank you so much. I didn't know you were there. So I have many of my seniors. Thank you so much. If you have any other question, you can always log into the academy and leave your question. I'm going to address your question anytime. So next month is another day. See you next month by God's grace.
Thank you.
Thank you.
Thank you all for being part of today's session of the Biostatistics and Research Methodology Program. We had the privilege of learning from Dr. Mojeed Akorede Gbadamosi, who guided us through the principles of inferential statistics and hypothesis testing, highlighting not just the theory, but also the practical applications that drive impactful research and public health decision-making. Your participation and engagement made this session truly enriching. We encourage you to continue exploring these concepts and applying them in your own academic and professional work. On behalf of the program team, we extend our sincere appreciation to Dr. Gbadamosi for sharing his expertise and to all participants for joining us. We look forward to seeing you in our next session as we continue to build capacity in biostatistics and research methodology. Until then, thank you and see you next time.